we're ready to start. Okay, thank you. So our next talk is Fair and Open Science for Earth Sciences with ESA and EarthCODE. And Krasen, we were just discussing the surname, but I'll let you do your own surname. But yeah, so next talk, and over to you.
Thank you very much, Paul. So today I'll be talking about EarthCODE, and what I want to get across is a couple of key points, which are how we see fair and open ecosystems, how you can benefit from them, and the tools and platforms we are building to help scientists and users get there. There's a Q&A forum thread that you can use later on for any questions that we don't have time to get to now. So what is EarthCODE? It's basically a bundle of tools and services that aims to support ESA and other earth science research communities in adopting fair and open science. Our aim is to accelerate scientific discovery by helping make data products and scientific workflows, and actually not just scientific, but any workflows that have value. So that could be something like efficient reprojections of data or interpolation, things like that, to make them more reusable and more reproducible. We also want to help ensure long-term persistent storage and research and reuse of research materials. That's both data and workflows. I used to be in academia, and you will find papers with my name that say the data is available here. And when you click on the link where the data should be, you'll find that the data is not there because no one's paying for the domain anymore. So we're trying to get rid of that and improve it. Also, something else that we have as a goal is to collaborate with the research community and with the open source community and not impose new platforms, new things, new tools on anyone, but get the best practices from what people are actually doing and make it easier for everyone to do that. So, for example, we're not developing new file formats. We're not developing new types of platforms. We're not developing different types of tools. We're working with whatever the community is using at the moment. Let's start with the data. Like I said, there's like a ton of really cool research being done. But it's actually hard to reuse it, and it's hard to fully understand it. And a lot of that difficulty actually can be addressed with a little extra effort from the scientists and with a little extra support that they can get from initiatives like ours. How we aim to do that, how we aim to make the research data more reusable is first, when a new data set comes in, we will try and give it a persistent identifier. Then we're going to store it on persistent storage. It's guaranteed to still work in 10, 20 years' time. We want to make it machine findable and machine readable. That's important because we don't want people to have to download zip files, set up their own storages, go to websites, have to create 50 different registrations, logins, and so on. And what we want to do is make the data interoperable. So that means that it has to follow, for example, CF conventions. If the data is satellite imagery or so on, it has to use interoperable formats, and preferably it has to use cloud-native formats so as to facilitate interoperability. With all of these platforms that we have at the end, which are all platforms that provide services to scientists, and they work with existing space agencies like ESA, NASA, JAXA, and so on, and they support research in doing their work. So ideally what we want is any of these platforms and any of these researchers to read the data and the workflows from any of the others. But the data is just the start of it. The whole vision is to have the open data, the open source code, then link them so that you can have experiments, which is something that's a lot more difficult than it sounds, right? Typically, you just dump a Docker file. But, so I was involved in a project where we were developing functionality to process hundreds of millions of building features. I was involved with one of the maintainers of GeoPandas was also involved in the project, and we also worked on, let's say, in PySal. Now, what was required for that project was updates to Shapely, updates to GeoPandas, updates to the PySal library. The build file for like all of this was, and we were using, I don't know, Pixie. Building the environment to actually generate the research required 10 different branches that were closed at one point when the changes got merged into the actual main repositories for Shapely, for GeoPandas, and so on. So all that code and all of these things disappeared from GitHub. You could have had it. You could have had the Docker file somewhere, but the Docker file would not have been. You couldn't have rebuilt the Docker file either, because all of the sources to build the Docker file would not have existed. Things like that. So actually linking data, workflows, and so on is actually very difficult if you want to do sort of open source properly, right? Like we did functionality whose place is in GeoPandas, is in Shapely. We shouldn't push our own like libraries and so on and build our own stuff on top of it if we know where it's supposed to go. But if you actually want to do it that way and you want to do reproducible stuff, managing all of that is just a nightmare. So we're trying to sort of, the vision is that by linking all of these, by following common workflow, language definition, and so on, it could help solve this issue. And then what we want to provide also is documentation and accessibility. That means that sort of anyone can run the things on their own locally, in addition to running the data on these cloud platforms. But if they can run it locally, and if they can run on some platforms, it could run on the others, and so on. And that's just the technical side of the whole thing. The other side is we don't want to create standards. We don't want to create new stuff. If something belongs in, let's say, one of the libraries that the community uses, or in one of the standards that the community already uses, we don't want to create new stuff. That's just a mess, and just brings more complication, more complexity that's not needed. So we have to engage with the people who actually build the tools, with the people who use the tools on day-to-day to actually figure out what are the best approaches forward and so on. And yeah, the idea is that EarthCODE can help do all of this with a bunch of simple tools and with a bunch of support for scientists. The main thing is that we'll be able to create data, tools, and compute that will be interoperable and replaceable. So something that works on one computing platform will work on another, and that every one of the computing platforms can have access to the different data and tools. We do this through specific tools. One thing that we call the Open Science Catalog, which just provides stack metadata for research outputs and workflows. Something called the ESA PRR, which provides long-term storage. And the compute is handled by partner EO platforms that are integrated with EarthCODE. How can people actually use this? Well, if you're a scientific project that's either funded by ESA or one of the national institutions, or you're just creating something of value, you can push new stuff onto the Open Science Catalog, onto the EarthCODE system. If you are a scientist or just a developer or something, you can use all of the index data. You can download it. It's just a repository for new research that's being funded by, well, you at the end of the day. And if you are one of the platforms, you can integrate into EarthCODE. Like I said, EarthCODE has a couple of, well, 4 pillars. One's the persistent storage it provides. The other one is the integrated platforms, the Open Science Catalog, and the forum. Now, the forum takes care of the community. Open Science Catalog takes care of the cataloging. The integrated platforms take care of the compute. The PRR takes care of the long-term storage. The important thing is that you should be able to use a lot of this stuff on your local or institutional infrastructure. And with a few lines of code, with a few changes, you should be able to scale your data on the EarthCODE platforms, right? So they should support all of the tools that you would be using on your own. you can have a look at the EarthCODE portal. There you'll find information about the overall project, documentation, what types of different platforms are available. We have around 7, I think. The website is currently being revamped. And then you can find a bunch of documentation. In the Open Science Catalog, that's a stack browser that basically catalogs all incoming ESA research, and it's going to get research from the UK space, from places like the UK Space Agency, NASA, partner initiatives, and so on. So any data, and you will also find there the related scientific papers and scientific persistent identifiers. You will also be able to find the workflows that scientists have used to generate their work. This is what it looks like. It's just a stack catalog. You don't have to use the visualizer. You don't have to do anything. It's just a bunch of JSON files that are hosted on GitHub. You can just download it, and you can manually go through them. You don't need any platforms. You don't need anything. Now, the integrated platforms where the actual compute happens integrate with the Open Science Catalog and with the ESA persistent storage to make sure that you can more efficiently read the data and process it. And every one of these has different advantages and disadvantages, but basically what's common among them is that they implement a common set of interfaces, and also they're used already by scientists. So we're not trying to push people towards a particular platform. Whatever research you're doing, you can just, the idea is that you can use whatever you're comfortable with, whatever you're already using. So for example, in PolarTap, they're using a lot of, they're focusing on the polars, right? They're focusing on North and South Pole. So a lot of research is done on that platform. On the EDC, on Pangeo, on the EDC, if you're having like Pangeo workflows that you're working on, so that's stuff like Jupyter Hub, Dask, Xarray, and so on. The idea is that you can just, there is a deployed Pangeo version on EarthCODE, and you can just upload your notebooks there, and ESA will provide, well, and you'll get the compute to do your work. How you actually get the compute is through negotiations and so on. It doesn't come for free, but what you can apply for is a network of resources sponsorship, which, depending on the project size, you can get a answer in about a week or so. So if you're applying for something large, for a lot more compute, it's going to take more time and so on. So and what every platform has to integrate is a single sign-on, a bunch of visualization tools, integration with the Open Science Catalog for publishing, integration with the Open Science Catalog for data access, and describing workflows and so on. And it actually has to be able to provide compute to scale research and resources. And yeah, so the idea is that once all of these, once you have a workflow on one system, they will be not just reproducible, but reusable on the originating platform. So you click on, with a click of a button, you'll be able to run an entire scientific experiment. And it should be reusable to different degrees on the different platforms, depending on how different they are. So for example, there is one of the platforms that's integrated is a hosted OpenEO version. There you just get the entire workflow graph, for example, and you can still run it on like a normal Jupyter Hub instance, but it takes a little bit more effort on your part. Again, I'm highlighting the network of resources sponsorship. If you're interested in, you can apply. If you're doing some scientific experiment, though I should say that priority will be given to sort of scientific work that's sponsored by either ESA or the national agencies or sort of scientific bodies in the partnering countries that you can see at the bottom. How the publishing process works is scientists would develop a research, and then they would package the research. And this is where we provide support. So actually, the big hurdle in my experience is not using any of these tools. I mean, generating a stack item from a netcdf file is automated. It's not that much work. The problem is actually understanding people's data, converting it to the appropriate format. That would mean taking 100,000 netcdf files and putting them into a ZAR file. Or, for example, there is a lot of interesting work, right, that's happening for carbon, right? One project that we're working on at the moment, they have 2 terabytes of data, which, fine, it's a lot. But the issue is that it's, again, hundreds of thousands of files, but they come zipped, right? So, and compressed. So to actually use them, you have to register on the website, have to download the file, you have to unzip it, and then use it. So you have to provision 2 terabytes of storage before you even use the data, even if you're interested in just like a very small area around, let's say, Portugal. We aim to ingest data going forward that actually is in cloud native format, that enables partial reads, that enables sort of cloud optimized access patterns. And we provide support to scientists to do that. You're not just going to be left alone. We have a technical team that helps with that. And also another thing that is a problem is getting people to follow standards. So that's, yeah, there's a talk later on about that. But it's about providing enough metadata and enough information to actually know how the data originated, where the data originated from, how it worked. And we also provide support for that so that the data sets are actually reusable and the workflows are actually rerunnable and reproducible on other things. So yeah, so you develop a research experiment, you package your research, and we support you in that. And then you decide whether or not you need persistent storage. We will, that's an option that you can have. If you need to host your data, you need to host it on one of the approved domains. So that's things like, let's say, Zenodo or Pangea or one of the national infrastructure cloud providers. So that would be something like the Czech Institute for Scientific Research Network. And only those data sets will be accepted going forward. At the moment, because EarthCODE is a new thing, if you go to the Open Science Catalog, you will find a bunch of old projects that have been copied directly over from the EO for Society web pages, and they will have some issues there. But once all of that is done, going forward, we'll only accept stuff that's actually properly formatted, properly hosted, and so on. We're going to create then basically the rest of the things that you see at the bottom. A lot of that is automated, and you don't need to worry about it, and it's like a technical process. But it's going to be, you create a stack item, you describe it on the Open Science Catalog with some data, and then you create a pull request in GitHub. If you're afraid of GitHub, there is a graphical user interface, so you don't even have to interface with GitHub. And yeah, whatever you're trying to ingest will be manually reviewed by a person. So the Open Science Catalog sort of is a curated list of data sources going forward. And yeah, you can have a look at some of the ESA PRR stuff. We already have some projects there. And we have a forum where you can discuss, ask questions, ask what you think should happen, and provide suggestions, right? So even though we work directly with developers, so for example, we have some of the people who develop Jupyter Hub working on the project. We have a lot of the Pangeo community, the people who work on X-ray, a lot of people who work on the discrete global grid systems and so on. They contribute to the thing. We want to hear from everyone. We want to hear from users. We want to hear from open source contributors. We want to hear how everyone thinks this is going forward, what tools we can change, what we should focus on, and so on. And yeah, so have a look at the EarthCODE. Have a look at the data we have. Any questions that you have, any suggestions, let us know. And I'd love to hear your thoughts about the entire initiative. Thank you.
Yeah. So we've got time for some questions. So has anyone got any questions? Yeah.
Yeah.
Wonderful. But if you look at an institution like the University of Leeds, it has, I think, the greatest number of research disciplines of any institution in the United Kingdom. I actually, for my sins, set up their data repository. I couldn't deal with 100 people like you, 200 people like you. Are you talking, say, with the genomics people? Are you talking with CERN? Are you talking with other disciplines? So an institution can have a wider view of data and some common interfaces rather than having to deal with 200 or 300 EarthCODEs.
Yeah, that's a good question. The question was, do we talk to other national institutions or
data disciplines,
data centers to sort of integrate standards and agree on stuff? If Fran is around the room somewhere, but so I know that there was the part of the CDRC in Leeds, for example, and one of the my colleagues who we did our PhDs together was involved in generating or migrating the data from the CDRC to the new health data service or something. And I learned at this conference that she was responsible for generating the data standards and so on for that data. So I will be talking to her. I learned this yesterday. But yes, we talk to that. We talk with also national institutions, like the German Space Agency have their own standards, and EUMETSAT also have their own standards. I don't have an easy answer. It's difficult. It's difficult, but we try to settle on something that's like flexible enough to cover all of the use cases, and then we don't want to impose something on the community that they don't use. So the last talk was about satellites. There are a bunch of projects that use MODIS data. For some reason, they love having individual, and I don't know much about MODIS, but what I've learned in dealing with some of the projects is that they like having their data split by tile, and every tile is a TIFF file. They don't want it to be a single file. They don't want it to be any other format, anything else. Our sort of standards support that. It will be harder. So you, as let's say someone who works from the genomic side, or like me who works from the vector side, I won't know immediately how to read that data, but I can get access to the files, and I can get access to the sort of cloud optimized version of the files as well. But yeah, that's more, I guess, of a scientific problem rather than we don't want to impose a common standard on the different scientific communities. I hope that answered the question.
Is it really reproducible science if you just run the author's code with the author's data?
It's one step, I would say, in the right direction, because we can't do it, even that at the moment. So
if they've made a bug in their code,
yes, that's
just
fine.
running their code isn't going to detect that.
Yes. But that's you can version if that's something that you want. But ultimately, right, like all of these, why they're ESA funded and so on, is because at some point all of the workflows and the data gets reviewed and the papers get reviewed, right? That's the hope, that whatever is scientific gets reproduced.
Can I just add a partial answer to that question? Yes, it helps reproducible science, because I can run my data set against your code and your data set against my code, because both are available.
Yeah.
That's what I think is reproducible. But just providing a runnable version of my code in a Docker file or on a remote computer.
Yeah.
You can run my Jupyter notebook. Excellent, but I made a mistake on line 4 and nobody's botted it.
Yeah.
Or I lost part of the Excel spreadsheet.
Going. We're gone. Okay, thank you very much.